Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Welcome to the latest IRIS webinar. This is your host, Danielle Sumi, speaking from the Incorporated Research Institutions for Seismology headquarters in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility that operates programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. And webinars are recorded and archived on our IRIS YouTube channel. So feel free, if you want to go back and listen to some things afterwards, please do. The webinar ground rules are only the presenters in this case, Doug and Bob, and I will speak. If you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the box on the webinar control panel marked questions. At the end, I will read your name and question to the speaker. If similar questions have been asked, I may combine or skip them. If the webinar crashes, which has actually happened once, I will reboot it and simply click the link you received by email when registering. At the end of this webinar, I will send out a short 5-minute survey via email. Your opinions and insight will help us to inform future webinars. One of the questions we'll ask if you're watching this remotely in groups, so if it's more than just you, please let me know. Today's webinar is part of IRIS's continued efforts to provide resources and tools that enable research and professional development. Our presenters today are Douglas Given, the USGS Earthquake Early Warning Coordinator, and Dr. Robert Michael de Groot, who's the ShakeAlert Coordinator for Communication, Education, and Outreach. Both are located at the United States Geological Survey in Pasadena, California. Doug is the first author on the revised technical implementation plan for ShakeAlert that was released as an open file report in early October. And Bob is the chair of the USGS ShakeAlert Joint Committee for Communication, Education, Outreach. We welcome their expertise today on the technical and the societally relevant aspects to the complex issue of earthquake early warning. So without further ado, here's Doug and Bob to talk about ShakeAlert, the path to West Coast earthquake early warning, and how a few seconds can save lives and property. So thank you, Doug.
And thank you, Danielle. The point of today is for me to give you an overview of the progress and status of the USGS-led efforts to create an earthquake early warning system for the West Coast of the United States. And that system is called ShakeAlert. The USGS has a very robust earthquake hazards program, and it has the mission to reduce deaths, injuries, and property damage due to earthquakes in the United States. And in order to accomplish that mission, we do many things, including assessing the long-term earthquake hazard. We conduct earthquakes into the research into the physics of earthquakes and the hazards caused by them. And then we provide earthquake monitoring and notification, and that's the category into which earthquake early warning fits. And then tied very closely to that is building public awareness, in this case specific to the earthquake early warning system. In order to accomplish those goals, we produce lots of products, and the basis for much of this work is the operation of seismic networks. So the Advanced National Seismic System is a federation of regional seismic networks in the United States, along with an overprint of a large backbone network across the United States, including Hawaii and Alaska. And the earthquake early warning capability of ShakeAlert is built on top of that already existing seismic monitoring infrastructure, the data processing centers, and the expertise that USGS already has with respect to earthquakes, monitoring of earthquakes, and very rapid data processing. If we look at a timeline of the types of products that are produced by USGS and its partner institutions, we can see that shortly after the earthquake occurs, early warning, of course, falls into those few seconds to tens of seconds immediately after origin time. But the products that we have been producing for years, and in some cases decades, include just location and magnitude of the earthquake, is generally done within about a minute or two after the earthquake starts. We have an event notification service where you can sign up for emails and text messages. We have about 800,000 subscribers to that service. And then very rapidly, within minutes, we produce estimates of ground shaking in the form of shake maps. We gather human information about the example or the impacts of that earthquake in the Did You Feel It map that you see in the center of this slide, and then an assessment very rapidly of the estimated fatalities and economic losses due to those earthquakes. So there's a whole suite of post-earthquake information, and ShakeAlert joins those products in order to reduce the impacts of earthquakes. So the basic concept of earthquake early warning is probably well understood by most people on this call. An earthquake begins at some location, and if you have sensors close enough to it, you can detect that earthquake very, very rapidly, and then send information out ahead of the advancing P and S waves. The velocity of the waves are shown on this slide, and of course the S waves tend to be of higher amplitude and therefore more destructive than the P waves. So the faster you can send out an alert, the more warning time potential impacted people will get. And of course, the farther away a user is from the origin of the earthquake, the more lead time they will get. So there's a very common question, well, how much warning can I get? And the answer, of course, is, well, it depends on where you are with respect to the earthquake. And of course, it also depends on the speed of the system. In areas where we have dense network coverage, the detection time for our system is typically 5 seconds, in some cases a little bit less. So after the earthquake begins, we can generally produce an alert beginning about 5 seconds after the start time of the earthquake. This project is focused on the 3 states of the West Coast of the United States because that's where most of the earthquake hazard is. This is an estimate done by FEMA, and you can see that about 3/4 of the estimated losses are in the 3 states of the West Coast. And in fact, almost 2/3 of it is in California. So that's where we are focused. But once we complete the ShakeAlert system on the West Coast of the United States, we do intend to propagate it to other high hazard areas. So this is a rather busy slide, but it gives you the gist of what is going on for ShakeAlert. The current network of sensors is over on the right-hand side, and I'll have a little bit more to say about that in the next slide. The color codes here are the speed at which the data arrives from the field sensors, and that's critical. Again, to achieve that 5-second alert generation time, you need the data from the field very rapidly. And most seismic instrumentation wasn't designed for that kind of speed, but at least not initially. But now the manufacturers are in fact creating capabilities that are that fast. And we need to upgrade existing stations and build a lot more stations in order to service this need for speed in ShakeAlert. That map also shows 3 red triangles with exclamation points in them. Those are our alert centers, and they are overprinted on top of the centers that were already in existence for the operation of seismic networks in the US. One in Seattle, one in the Bay Area, and one in Southern California. Now the blue box and arrows picture in sort of the center left is a schematic of the steps needed for an earthquake early warning system. So starting on the left, you see there's a sensor network. Obviously the map is showing that. And then the data needs to come in very rapidly over a system of telemetry, labeled here as field telemetry. The box in the center is deceptively small and simple because that's where a lot of the complexity really lies, is in the data processing and the alert generation. But once an alert is generated, there's another telemetry problem, another data problem, and that is delivering the alerts to those who need them. And I'll have more to say about that later. And then, of course, it's useless to send alerts if people don't know what to do with them. And so there's user action and actually a significant amount of user education and training necessary in order to realize the full potential of a system like this. The text down the bottom is basically a history of how we got to where we are today. The USGS began funding research and development in early warning in around 2006. We went through several cycles of demonstration and then going into production prototype mode, first in California and then in 2017, a full West Coast prototype. And this year, we have turned the corner on a significant milestone that we're calling phase 1 of limited use. And so, as Bob will describe later, we have about 40 pilot users who are actively using the alerts, and we are anxiously courting many, many more to begin using the data and the alerts from the system. We've also made some significant technical improvements to the system to go along with that milestone. Full public alerting, however, still awaits several things, including full funding, which we do not yet have, full build out of the seismic network, which we still have not attained, and also some technical limitations, particularly with respect to the delivery of the alerts, which we'll talk about as well. And then, of course, complete user education and training, which is also an important component. So the seismic network is shown here, and the progress that's being made. Our plan is to build 1,675 stations on the west coast of the U.S. A typical free field station is shown schematically center left, and a photo of a field station in the lower right. You'll note that this one has a GPS radome antenna. Not all of them do, but some of them are seismic and geodetic co-locations. These two maps show the progress that we've made over the last few months. And the red dashes show that we've concentrated our efforts in the metropolitan areas so that we have reached target density in Southern California, the Bay Area, and Portland and Seattle areas. So that's where our alerts are fastest. Now, that does not mean that we can't do alerting in these other areas. It just means those other areas, the alerting is slower and less reliable. Now, that's the seismic stations. We do plan to include GNSS, or GPS, as some people know it a little more readily. The inclusion of the GPS stations are important for the extremely large earthquakes to characterize the extent of the rupture. Now, the inclusion of GPS will not speed up the process, but it will make the product better. So you can see a map of the geodetic stations that already exist, and we really don't have to build very many new ones. There are already a lot of geodetic stations on the West Coast, and our main task is to upgrade them and to telemeter them so that the data can come in real time. So we have a network plan to add 10 stations in Oregon, upgrade 275 in California and 130 in the Pacific Northwest. But we should end up with almost 1,200 geodetic stations contributing to the system. The geodetic processing will happen in 2 locations, Central Washington University and USGS Menlo Park, and then those data streams will be fed into the 3 centers in Seattle, Northern California, and Southern California for inclusion in the alerting process. We have 3 algorithms that are currently candidates for use and integration into the ShakeAlert system for geodetic data, and a comparison will be done among those. It should end by the end of this year. And then we'll either choose one of those for integration into the system or merge them together. Now, this is a complex diagram, basically the internals of the system, and it's actually a simplification of the internals of the system. The data flows from the bottom of this diagram upward. I'm not going to go into a great deal of detail, But you can see that there's a data collection at the various geographic centers where we run network operations. It goes up to that center part, the production layer. All of the intercommunication in this system is done through a messaging middleware open source product called ActiveMQ. And so once you get into that middle layer, every geographic center has access to all of the parametric information that's derived by the waveform processing. So that means we actually have not just 4 as shown here, but at each center there's a redundant server behind it. So we actually have 8 production processing machines that are all all have access to the complete data set and are producing the answers that we need. So there's a great deal of redundancy built into the system. Once an event is detected, it pops up to the top layer, which is shown here as the alert layer. And there are 3 systems shown here. There's actually 6 because they're redundant. And that is where a decision is made about whether or not an alert should be issued. And then subscribers, users of the system, attach to one of those 6 servers, or all of them if they like, in order to get the information that they need. Now, a little bit on the earthquake physics of this problem. Here on the West Coast, we have 3 distinct types of earthquakes that we need to detect and alert on. And those are shown in the left-hand block diagram in the tan balloons. We have shallow crustal earthquakes, and those are the types that are more frequent and actually more common in California than they are in the Pacific Northwest. And particular to the Pacific Northwest, where there's a subduction zone, we have 2 additional types of earthquakes. The plate interface earthquakes, which can be very, very large, like Tohoku was in Japan. And then we have the intra-slab earthquakes, which are very deep, but can be very dangerous because they can be right underneath the population centers on land. The Nisqually earthquake in Seattle was an example of that, and the Mexican earthquakes about a year ago were also intra-slab earthquakes. So we have to worry about all 3 of these types. And then, as you can see on the right, we've got shallow crustal faults throughout California, and therefore we have to completely cover California because and the Pacific Northwest, because we're not sure where the earthquakes are going to be. This is not a simple problem. We can't say that all the earthquakes will happen over there, and we're trying to protect this city over here. We have earthquake sources everywhere on the West Coast and population everywhere on the West Coast. A little bit about the earthquake physics. This animation is running 12 times real time. It's showing a model of a rupture on the southern San Andreas Fault, originating on the southern end of the San Andreas and rupturing northward towards the population center of Los Angeles. One thing that a lot of people don't understand is that earthquakes don't happen at points, particularly big earthquakes, that they rupture long faults, that they take a long time for that rupture to happen, and that you can't predict whether the fault is going to break just a little bit and have a small earthquake, or continue to break a long length of fault and end up creating a large earthquake. And so alerting becomes a challenge there, and you must continue to monitor the earthquake rupture as it occurs and update the area that is likely to be affected very rapidly in order to get the fastest, most effective alerting. And then finally, note here that the rupture gets closer and closer to the downtown Los Angeles, where those 2 yellow arrows converge. And the result is that it matters a lot more where the fault ends up and how close it gets to you than it does where the earthquake begins. So how much warning can you get? This is one way to characterize that. Again, the red stars in Los Angeles, and the contour lines indicate the amount of time you would get if an earthquake occurred on one of those blue contour lines. And so, clearly this shows you that the farther away the earthquake is from you, the more warning time you get. And it shows you a little bit about the impact of the stations and the station density on shore gets you more warning time than an earthquake that were to originate offshore. But you can see that warnings on the order of tens of seconds are quite practical in this kind of situation. Now there's a nuance that needs to be understood. So here's an example of a hypothetical earthquake on the Hayward Fault connected with a large project that was done recently in the United States. The epicenter is shown at the orange dot on that map. And we're going to assume that we're at the location of the red star, and that's about 120 kilometers away. So in this instance, the very first alert happens just about 5 seconds after the earthquake starts, but at that time, the earthquake hasn't grown to its full size. And so the system detects it as a magnitude 5.5. Does an estimate of the contours encapsulating the modified Mercalli intensity levels, in this case going up to about MMI 5 or 6. And if you are at that red star's location, you would get about 25 seconds warning before the S wave arrives. However, the system is telling you that you can only expect an MMI 2 intensity to affect your area. And it's really quite modest. And so you might elect not to take any action at that point. But if you wait for the event to grow larger, then you lose some of your warning time. So if we step through here, you can see a few seconds later, the event estimated magnitude is up to 5.6. But you've lost a few seconds. But now you're sure, okay, now it's going to be MMI 3. What is my threshold for taking some kind of action at my location? And the longer you wait, the more certain you are it's going to shake you hard, but the more time you lose. And so about 14 seconds after the earthquake began, we're up to magnitude 6.5. We now know that our location is going to experience MMI 4, but now we've only got 17 seconds. And if we wait to be sure that it's going to shake me at MMI 5, we are too late. The S wave has arrived. And so the moral to this story is to optimize the time, you must be willing to take action at a relatively low MMI level and therefore sustain what appear in many cases to be false alerts. So there's always going to be a trade-off that's specific to the user, and the actions taken by specific users may need to be customized according to their tolerance for taking that action, the cost of taking that action. And so that's pretty much up to the end users to decide when they should take their protective actions. Now, estimating these ground motions is also not trivial. Many of you are probably familiar with ground motion prediction equations and how difficult those can be. This diagram shows that difficulty. The scatter plot are reported felt reports from the South Napa earthquake of 2014. And you can see that there's a significant amount of scatter in what people report to have experienced as a result of that earthquake. And so given the fuzziness of calculating the expected ground motions, that is why the alert polygons in this diagram are really only very simple 8-sided polygons. Trying to do some kind of sophisticated estimate of the ground motions is really not worthwhile in this situation. And so it's quite generalized, not to mention some of the alert pathways and the consumers of the alerts can't really adequately handle much more detail than this. Now, detecting earthquakes in just a few seconds is a challenging thing to do. Our sensors are quite sensitive, and therefore they pick up ambient noise. They pick up regional earthquakes, and they pick up large distance earthquakes called teleseisms. And so these are just a few examples of the kinds of ground motions that occur and that have to be filtered out. And a lot of work and a lot of tests and analysis goes into the algorithms that detect the earthquakes in order to filter out these kinds of spurious noise examples so that we don't send false alerts. Teleseisms in particular are problematic, particularly deep teleseisms. So just give you a flavor of that. Is this an earthquake? If you look at those waveforms in the little blue oval, well, in this case, yes, it is. It's the South Napa earthquake, but there are many instances where just random noise can correlate and appear to be an earthquake, and that's difficult at times to filter out so that you do not produce false alerts. In order to tune the system and make it as good as possible to not miss earthquakes and to not produce false alerts, we have a very rigorous testing regime on our testing and certification platform. We have a set of more than 100 earthquakes and noise events that we replay and test every change we make to the system. So we do not make a software update, we do not make a configuration change to the system without running this full test suite through the proposed revision to the system before we deploy. In addition to rerunning the historic events, we also run any proposed change in a parallel system in real time on current data for a minimum of 2 weeks before we will deploy it into production. And this platform is also moving toward a capability where it will be able to assess not just the solution, but also the ground motion results. And that will also be evaluated to determine whether a change to the system is an improvement or not. Well, so what is the actual product of this system? And there are actually 3 primary products, and they're all in the form of XML files. So as I showed in that wiring diagram, the end users connect to our servers and they subscribe to various message types, and there are 3 which are listed here. The event message contains the earthquake source information. If the earthquake is relatively small, it's a point source solution. However, it can also include a finite fault solution. And so we've recently added an algorithm to the system that tracks the fault as it grows and sends as a line source the fault dimensions in that message. And then added recently to our version 2.0 of the system just a little over a month ago, we now have 2 different ground motion products. One is a contour message shown on the far right-hand side, those 8-sided polygons that encapsulate MMI levels that we estimate are going to result from this particular earthquake. And if you want more detail than these 8-sided polygons can give you, there's a third product, which is a grid map that you can use, and you can interpolate between the points of that grid map to get more detailed information about the ground motion estimate. And of course, if you've got GMPs of your own, or you know something specific about the site response of your factory or your facility, you can always do your own ground motion prediction. When we think about who the consumers are of earthquake early warning, they fall into 2 major categories. The first, of course, are people. And what they can do is they can drop, cover, and hold on. They can move away from hazardous areas, do a number of things to protect themselves or the people around them. And then the second major category is automatic actions. We are connected to 2 rail transit systems, Bay Area Rapid Transit in San Francisco area, and the Los Angeles Metro system in Southern California. And there are several water systems now that are connected to our system. And so there are lots of automatic things that can happen to protect infrastructure and property and people from the effects of the strong ground shaking. We put together a social science working group to say to determine what is best to tell people when we can send information directly to people, say over a cell phone message. And this is a preview of what that is. The bottom line is keep it simple. The seismological community has a tendency to want to say lots of numerical things. You know, what's the magnitude? What's the expected MMI shaking level? When is it going to arrive? But the social science tells us, no, that's just confusing to people. Just say there's an earthquake, expect shaking, drop cover and hold on. That is the message for people. So how do we get that message out to people? Well, there are a number of technologies. The one that most people expect us to use here in the US is the wireless emergency alert system. Now that's a system that's run by FEMA, the Federal Emergency Management Agency. The larger system is called the Integrated Public Alert and Warning System, which sends those alerts then to television, radio, cell phones, and a number of other portals. But the system sending it to all of those places was not designed with earthquake early warning speeds in mind, and therefore it is quite slow and really not fast enough for earthquake early warning. In fact, we're now trying to get a handle on exactly how fast it can go. We got some information from a national test on October 3rd, and with the help of Cal OES, we're going to be doing another limited test in the Oakland area, possibly later this month or early December, in order to determine how fast these alerts go. Plus, we have been working actively with the cellular industry to develop protocols to speed up the alerting through that system. Right now, we think it's somewhere on the order of 10 to 15 seconds of delay for the alert to arrive on a cell phone after we pass it to the system. So here's a list of the 3 mass notification technologies that are most promising. I've already described the one at the top, which is cell broadcast, the iPAWS WIA system. The speed, as I've said, is uncertain, and we're trying to get a handle on that, but we may be able to speed it up. But even if we're successful in using this system, the sound that it makes is the same, whether it's an earthquake or an Amber Alert or a weather warning or a fire notification. And so we hope to be able to get a specific earthquake sound so that we can train people to react almost reflexively when they hear that sound. The other thing that people say, well, why don't you just do an app? You know, push notifications. I get tweets, I get stuff over Facebook Messenger, I get all sorts of things. Why don't you just use that? And the problem, again, is those systems were not really designed with early warning speeds and volumes in mind. How do you send a message to millions of individual subscribers, potentially, in a couple of seconds? And so in order to determine whether this is even possible, we're doing a test with the city of Los Angeles and with a few others to try and determine the actual capacity of push notifications to cell phone apps to carry the earthquake early warning. And then there's a third technology which is in development but not quite ready for prime time, and that is called data casting. It is using the existing television broadcast signal from public television stations and encoding the alert in that broadcast signal. Now, that doesn't mean that it'll pop up on a television if you happen to be watching public television, but instead it means that signal will be out there in the airwaves to be picked up by any receiver that is tuned to the right frequency and has the right decoder software. And so it would require a special built receiver in order to decode that message and take some action or alert a human. So that is in the works and not yet complete, but it does be very promising because it doesn't depend on the internet. When we send messages, we will also follow them up as soon as we have a much better idea of what the earthquake was, after we have more data and have sort of settled on its final location and magnitude and impact. So in the case of a true alert, which we hope is most of the time, we will send a follow-up telling people, okay, we told you to drop, cover, and hold on, and here's why. There was a large event over in this location. So to give situational awareness so that people can take then the next steps of what they should do after the earthquake shaking subsides. And of course, we anticipate that there will be false alerts. No system is perfect. And so we will also send as quickly as we can and as quickly as we determine that a false alert has been sent, information to cancel the alert, and as soon as we know it, an explanation of what happened. And that's largely to reassure people that the system is well run, and so that they don't lose confidence in the system in those rare cases when we do issue a false alert. Okay, I'm now going to pass the baton over to Bob DeGroot, who's going to tell you more about the user community and the education and outreach component of the project.
Hello everyone, I'm Bob DeGroot. I'm the Coordinator for Communication, Education, and Outreach for ShakeAlert, and it's my pleasure to tell you a little bit about this component of the program. Doug has mentioned a couple of times during his talk about that ShakeAlerts would not be at all useful unless people and things knew what to do, and so this is a very, very important component. Another piece that I think that's key here, and a part that I'm involved in as well, is working and engaging with our user community, which ranges from individuals to large corporations wanting to do very large-scale solutions. And I work with a group of about 6 folks across the West Coast in California, Oregon, and Washington to recruit and to onboard and to care and feed of these different partners. So if you recall earlier in Doug's talk, there was a flow chart where it showed sort of the first thing, of course, the detection and characterization of the earthquake, and then eventually to where a shake alert is published or produced. And it's one really important piece to emphasize here, that the USGS is responsibility at some level. I use that word kind of loosely, but we are responsible for producing that alert, and then we hand it off to our partners for distribution. And that's a key thing. And so this project, I think more so than many others the USGS has been involved in, is engaging a large community to build an earthquake early warning industry. So this list that you see on this slide is about 40 different partners. There are actually more that we have included since this list was first published, and we are continuing to grow it. And we want to test ShakeAlert. We want to use ShakeAlert. We've been spending a lot of time testing ShakeAlert, but now going into an operational phase and using ShakeAlert in as many authentic environments as possible. In 2018, we focused on 5 sectors, and those 5 sectors are emergency management, utilities, transportation, education, and healthcare. And we wanted to really work on bringing high impact, high visibility groups and get them working and developing. But we're working with a total of about a dozen or so sectors to use ShakeAlert in as many environments as possible. And we kind of have 2 major flavors of technical partner. We have those who are where ShakeAlert is actually applied in an environment, a real sort of rubber meets the road environment. And then we also have a class of partners who are building the widgets. So one of the things that I think that is to be considered here is that we need an industry out there that can develop these off-the-shelf things that can be plugged in, that can be installed, so that ShakeAlert can be as broadly applied as possible. So you see the list there, and you may have seen in the news work with BART, for example. We did a test in the early part of October where we slowed down a BART train, and one of the interesting things that came of this test was the fact that people said, well, we really didn't notice anything. This is sort of anticlimactic, right? And actually, that was the idea, is that we wanted ShakeAlert to intervene in the process of the writer experience, but make it seamless, to make it part of the writer experience, that it's something that's happening and not something that's going to, bells and whistles and flashing lights are going to go off, but actually it's part of that writer experience. So there's a lot going on in this area. We're continuing to grow our partnership base as we speak. Let's go to the next slide, please. So I spoke about relationships, and I'm not going to spend a lot of time talking about these different relationships, but part of my role with ShakeAlert is to build agreements between our partners and the USGS, and it starts from folks who are just simply interested in knowing what ShakeAlert's all about. They want to have access to our active MQ data feed. They want to know what the signal's all about. They may set up a demonstration console called User Display, which visualizes ShakeAlert, just to get a sense of what it's all about. And we use this as an onboarding technique to get people interested and thinking about things that they can be doing. And so what we're doing is we're working with a class of partners who are now coming up with those creative and innovative ideas to apply ShakeAlert in authentic environments, and that's where they move into the developing phase. And once, over time, and we have a few partners who have gotten to this point as of now, where they have demonstrated their ability to handle some really significant real-life applications for ShakeAlert, and we've provided them with what's called a license to operate, and that enables them to be able to essentially go into business, to market their solution out in the marketplace. So it's a very, very interesting enterprise to see this all happening, and there are a lot of really creative ideas to use ShakeAlert in environments. Let's go ahead to the next slide, please. So one of the major pieces of ShakeAlert, and Doug talked about two things so far in his talk. He talked about a message that would come over the cell phone, the earthquake, expect shaking, drop, cover, hold on. That messaging and that process actually comes out of our very extensive multi-state communication, education, and outreach program. And the other piece that Doug talked about as well, of course, is post-alert messaging. This is another piece. So we want to provide a lot of resources for our users and provide guidance to potential users to use these resources in a way that will make ShakeAlert the most effective program possible. And so we've convened a group within the context of ShakeAlert called the Joint Committee for Communication, Education, and Outreach. We have participants from California, Washington, and Oregon. We also have participants from British Columbia, and we are working on a whole variety of different pieces with us. And one of the biggest pieces that I think is most visible at this point is our social science work that we're doing, especially in the areas of looking at messaging and sounds. What will if you get a ShakeAlert on your phone, for example, what will be that sound? And will that sound like something else that you get, like an Amber Alert? And so the social science that we've learned, and we've worked with many, many investigators. In fact, one of the topics for a previous IRIS webinar was about the IDEA method. Deanna and Tim Sell now gave a wonderful webinar about some of these topics, and one of the things is having a sound that one can immediately identify as being a ShakeAlert. So you don't have to pull your phone out of your pocket or out of your backpack to say, well, what is that? Because Doug has been talking a lot about latencies, about the time from earthquake detection or earthquake origin to eventually ShakeAlert production and delivery. Part of that process at the very end, of course, has to do with the latencies associated with things and people taking actions. And so we want to reduce the human latency component by identifying a sound, for example, that will provide a cognitive shortcut, so to speak, where that sound will immediately be associated with a ShakeAlert and people can take an appropriate protective action such as drop, cover, and hold on. So this is a really big piece for us. And if we go to the next slide, I'll give you a sense of who's involved. I'm not going to talk about all these people, but and I know this is maybe just a sort of a boring organizational chart, but it's something that I live with every day because I rely on all of these people from the 3 states and British Columbia. We have representatives from the state geological surveys, the offices of emergency management from each of the 3 states and British Columbia, and we also have representatives from our universities. And the representatives from the universities, from Caltech, Berkeley, Washington, and Oregon, are actually very much involved in the technical partnership piece that I mentioned at the beginning of my talk. But the bottom line here is, if we go to the next slide, is that this group that I just showed you on the previous slide is now represented in the green box on the right. That's our national committee. We have this group of people. They convene on a regular basis about every 2 weeks to talk about big issues. We also have larger community calls, which if you're interested, if you're on this webinar, if you're interested in participating and learning more about ShakeAlert, you're certainly welcome to join us. I'm going to also put in a plug for Danielle, who is our host today, because she actually is very much involved with ShakeAlert at this point, and I'll let you know a little bit more about what she's doing with us in a bit. Iris in general is involved, and Danielle is our representative. But the one thing that's a key takeaway from this slide is that the ShakeAlert system is a West Coast system, but there's a lot that we want to make sure that we take in consideration. We know that each of the 3 states, and of course I know that I've included British Columbia in the mix in this talk, but we're really implementing things with the 3 states, California, Oregon, and Washington, and we know that each of those states have priorities, they have needs, they have concerns, and we want to be able to address them. Their method of implementation may be slightly different, but the one thing that we want to maintain across the states is as much as possible, is consistent messaging and consistent education and training, because we know that people move across states all the time. We know that people routinely visit those 3 states. Some people have family and they work in one state and they live in another. So we want ShakeAlert to look and feel the same in all 3 places, and this requires a considerable amount of coordination. So one of the things that this takeaway from this slide is the fact that there is as many as possible pathways of communication between the states and the national committee, so that we can make sure that we're all on the same page. And it's been a massive enterprise, because we're working with a number of different agencies from all 3 states, and also of course we're working across the USGS as well, which is an important piece as well to mention here in a bit. The other thing is, you'll notice under the JCCO committee, where there's my name below it, there is a series of initializations below them, TUWG, ERWG, and so on. These are a series of working groups who are involved in permanent roles in addressing the major issues related to ShakeAlert communication, education, and outreach. And one of them that I've already talked about at length is the technical engagement and basically utilization of ShakeAlert in these different environments. And that's, so we have a technical user working group which addresses these issues. We also have an external affairs and public information working group where we're coordinating with all of the public information and media folks across the 3 states to make sure that our messaging is consistent. And there's a really big chunk of this that we've been doing and developing talking points and a whole number of other products to make sure that we're communicating ShakeAlert consistently across the states. We've also stood up our Twitter account, which the listing will be in one of these slides a little bit later on, but you're welcome to join us. So there's a lot going on, and our friend Danielle Sumi, who is our host today, is involved in the Educational Resources Working Group. In fact, if we go to the next slide, I think it's on, yes, it's right here. We have basically developed a comprehensive 5-priority communication, education, and outreach plan for ShakeAlert, and they fall across the major areas of concern. So this plan was not created in a vacuum, but literally it was something that the community itself developed, where we started very early on with a few focus groups and then got people together to discuss these things. So they fall across all of the different pieces: public safety and preparedness and resilience, technical implementation. I think those are 2 obvious ones. The third, consistent messaging and communication, having to do with making sure that we're developing messaging that's consistent, and also the messages that we use to talk about expectations related to ShakeAlert. And Doug talked a lot about expectations during his talk. We need to be very clear with folks what ShakeAlert can and cannot do. Number 4 on the list, I think, is key and probably hasn't been discussed extensively during this. It was implied but not discussed during this webinar, is that we want to communicate that ShakeAlert is not a panacea. It's not going to solve all of our problems, but yet it's one of the tools in the toolbox to reduce earthquake risk. And so we would like to use ShakeAlert in concert with all of the other products produced by the USGS and also our partners to reduce earthquake risk. And that's a key takeaway from all this, is that it's one piece in a very, very important array of resources that we're making available to people. The last one on the list, and this is where Danielle is involved, our science education initiative. IRIS, of course, is very well known around the world for its excellent education and outreach products. We're working with Danielle and John Tabor and some folks out west, Jenda Johnson and also Bonnie Magura, to develop a suite of resources. And many of those resources already exist, but they're going to be repurposed and reconfigured for use with ShakeAlert. And we know that they've been tested and they perform well. There's no reason here to reinvent the wheel, folks. So we're doing a lot of work in this area. So it's been very productive so far. Next slide, please. So I mentioned very briefly the whole idea of having an effective communications plan. You'll see our Twitter account name there at the bottom. Please follow us. Please comment on what we're doing. Please ask questions. We want you to get involved, be a part of the conversation. We also have other ways of getting involved with ShakeAlert. We're out there to find more partners in a whole number of areas, including our communication, education, outreach enterprise. We have an array of really excellent folks working with us from across the agencies, but we know that ShakeAlert will only be effective if we have wonderful partners like the ones we've already engaged, and also many of you who are interested in joining us. And I think that does it for me. Thank you everyone for your attention, and look forward to your questions.
Well, excellent. Thank you both, Doug and Bob, for your excellent presentation. So please go ahead and write any questions that you may have in the questions chat box. Some people have already done so, so I'm going to start there already. So this question is for Doug from George Kaviris. Asks, could you inform us on how you calculate MMI? Do you use a relation with magnitude and distance, and how reliable is it?
Yes, we use a fairly standard ground motion prediction equation, GMPE, and it's our goal to make it as close as possible to our other products, especially ShakeMap. Now we had to do a few things to make it fast, but that is the goal, to do the same sort of model prediction based on source information as is used in a ShakeMap, if in a case where a ShakeMap doesn't have any ground truth or amplitude information from the surrounding sensors yet. So it's a model only prediction using the same GMPE methodology as is used in ShakeMap. The question about how accurate it is, as I showed in one of the maps, we understand that there's a broad range of human experience, and that's what MMI is primarily about. You know, some people are awakened, some people become alarmed, and so forth. And it, you know, we could do a more detailed mapping, as I suggested before, but it would basically be false precision, because there's going to be a great deal of variability depending on your situation and your soil conditions and so forth. So anybody who wants a more precise estimate of ground motions should take our source information and then apply their own ground motion prediction methodology and their own site corrections.
Great, thank you, Doug. This question is also for you. It was just about the magnitude 7.8 like shakeout scenario in Southern California, that animated GIF that you showed. Is that widely available? Where could we go find it?
The animated GIF?
Mm-hmm, yeah.
The more precise or higher resolution version of it is available on the web. I believe it's at the SCEC website. Frankly, I stole the animated GIF from the LA Times, who turned it into that format.
Oh, awesome.
So the the full, this is Bob, the full animation of the magnitude 7.8 shakeout scenario for the Southern San Andreas is actually available. It's a USGS product, but it's available, widely available on shakeout.org.
Excellent. Great. That's a good transition because there was another question from Liam Harbert for you, Bob, about the Japanese and if they had already defined a sound for earthquake and tsunami alerts already, because you talked a lot about the sound. And
yes.
Yeah.
So the question is developing an appropriate sound, and one of our, and I didn't speak too much about this there was a slide about this, there was a series of letters next to one of the org slides, and we have convened a series of focus groups, and within the Joint Committee for Communication, Education, and Outreach, we have these very short-term groups that get together to solve a very specific issue, to produce a very sort of very specific deliverable. And one of the groups that we convened had to do with what qualities, what would a cell phone do when it received a shake alert. So a push notification, what would the phone do in terms of sound, what would the writing be on the screen, and all those sorts of things. And so we investigated the sound issue, and we did a literature review and found out what qualities are necessary for a good sound. And of course, one of the groups that we have to take into consideration are people with disabilities, access, and functional needs. And so we wanted to make that a consideration. Now, this is not really getting to the answer to the question. So we found that an ideal sound initially was the Japanese NHK chime, and I don't have it available to play for you out loud here. But one of the goals here, and as I said during my talk, is we wanted to make as much as possible things consistent across the 3 states, messaging and sounds. Well, we actually talked to the Japanese about potentially using the NHK chime as the shake alert sound. They declined our offer, so we are working currently with the California Office of Emergency Services and a social science researcher to develop alternative sounds. So we wanted to use the NHK chime because it's ideal. It has that international quality to it because I know that it's also used in Chile, and so we wanted to go that route, but it didn't quite work out. So I hope that answers the question.
Yeah, I think so. And I think a follow-up question is from Marino Prodi. Wanted to know just like how effective is it using a repeating word? I know that you showed like the alert that would go earthquake, earthquake, shaking in so many seconds. Instead of like a sound. So what's the trade-off there, I guess, between the repeating words and like a specific sound?
Well, as I mentioned during my portion of the talk, is that the sound itself is going to provide that cognitive shortcut. So we want a unique sound that would be identified with a shake alert. And that's a training issue. So people have to know that making the connection from the sound to the actual action. And so the repeating of the words is actually something that was recommended to us by our social science advisors, that hearing it twice will, you hear it once, you may not have the attention, and by hearing it the second time, you actually have that attention. But remember what we advised for qualities of a device like a cell phone, and I'll say this because I don't know if it was said during the talk. We're not just expecting to have shake alerts being delivered by cell phone or by on your radio, but we want it to get to you by every means available. And the whole idea is that you get this through multiple modalities. The idea of what a cell phone does is that we said, okay, if we have this particular condition, we want the cell phone to do these different things, something that someone can read, something that someone can hear. We want to provide as many opportunities as possible for people to understand that it is a shake alert that they're getting. And one key point about this messaging that I think that we need to emphasize as well is that Doug said something really important, is he said that it needs to be brief, it needs to be right to the point. So a key component of this message, rather than providing information about MMI or magnitude, we just want to tell people what to do. So we need to provide something that's actionable. And that's a very important piece of advice we've gotten from our social science community.
Great. Thank you, Bob. I think this question is for Doug, but you both might be able to answer it. This is from Panina Miller. She asks, you mentioned that all 3 alert centers receive all the data when an alert is generated. And then do all 3 centers then send out an alert? And if not, how do you decide which one sends the alert on to the dissemination partners?
Assuming the system is functioning as designed, they are all independently generating the same answer. And that way, if there is a loss of communication among them, then you can still get the same answer from any one. So again, it's designed with redundance so that it will bend but not break under duress. So you should get exactly the same answer no matter which of those servers you are connected to. And if there's a system failure, if it's severe enough and the server that you are connected to goes dead and there is a constant heartbeat that tells you that it's alive. So if you lose that heartbeat, then your client software should then automatically transition to one of the alternative alert servers. So that's the way the thing is designed.
Okay, great. Are there any, so this is from Joe Ferrugia. Are there any plans for real-time sensors offshore?
They're really expensive. We actually have some offshore sensors right now, but they, again, were not designed with the kinds of speeds that we need for earthquake early warning. Those are part of the Neptune array off the coast of the Pacific Northwest. There are also some issues with national security, and the offshore sensor data needs to go through basically a filter so that we're not detecting nuclear submarines coming out of Bremerton. So there are some issues related to offshore sensors, the expense of running them, and the security thing I just mentioned. It's on our list of things that would be desirable, but frankly, we don't even have everything we need onshore yet. So we're not yet seriously considering offshore unless there's a scientific reason and scientific project that would make that possible.
Great, thank you. This question is also for Doug. This is from Bob Crosby from Ocean Networks Canada. What is the minimum number of sensors that must detect a P wave before earthquake processing begins?
Well, I'll restate it just a little bit differently. We will not declare a trigger unless 4 stations sense the ground motion. And that requirement that there be 4 stations voting that they think an earthquake is underway is empirical. It's based on sort of tuning the system to minimize false alerts while maximizing alert speed. If we could guarantee that our sensors would not have noise spikes or ambient noise issues, then we could reduce that number. But the reality of the situation, based on experience, is that we found an optimum point at 4 sensors.
Great, thank you. This question is for Bob. It's from Shelley Olds. What integration is currently being planned for tsunami alerts?
That's a good question, and we're working on that, and that's really being done in collaboration initially with folks from the emergency management agencies in Washington and Oregon. So it's something that's on our list. I don't have a long answer for that. I know it's something that's of great concern for especially our colleagues who, and I'd also like to make sure that we don't forget California, which also happens to be in Cascadia. But it is something that's on our list to work on. And in fact, in the development, and we're embarking on a very large campaign to develop resources, materials, and also education and training and a communication strategy that's going to take coastal communities into consideration and how we work with the two. Now, the technical side of that, that's something that I'm not too involved in, but as far as the education and training piece, it is something that's at the top of the list of our colleagues who are concerned about people along the coast.
Yeah, when you think about the early warning system, it really is just giving you information maybe tens of seconds to a minute sooner than you would have had it otherwise. So if the current guidance is if you feel an earthquake and you're near the coast, or if you get information that there was a large earthquake and you're near the coast, take the appropriate action. And that doesn't change with early warning. You just do that a little bit sooner than you would have otherwise.
Yeah, and that's a really good point. And we have been working very closely with the Los Angeles Unified School District, the second largest school district in the United States, and the emergency manager from LAUSD, Jill Barnes, really characterizes ShakeAlert as doing what we already do, but doing it sooner.
Right, great. Alex Becerra asks, this is for Doug, due to delay consideration and number of stations, are commonly used protocols like SeedLink to transfer the data from the sensors to the data center enough, or did you have to create a new communication protocol?
The short answer is SeedLink is too slow. We use a variety of protocols, including this is getting wonky, folks. Sorry, Earthworm and the native protocols on some of our hardware out in the field. We prefer Q330s. We have Obsidians. We also have Etna 2s, and we have some Nanometrics Titans. But all of those manufacturers have now adapted their internal protocols to very fast data transfer speeds, primarily motivated by early warning requirements.
Great. Rui Chen asks, this is also for Doug, if you could just clarify that the warning time is based on epicenter distance, not rupture distance.
Most of the graphics that I showed were based on the epicenter. I'm not quite sure the context of the question, but given that the alerting happens very quick, right after the initiation of the rupture, it's still a point source pretty much at the time we issue our first alert. But as the fault length grows, then the alert polygons would also change in shape to adapt to that longer rupture. So I'm not sure if I'm quite answering the question, but I'll try it from the start again. When the earthquake begins, it is a point source. We're triggering before it grows to anything bigger than a point source, and so the initial alert, at least, is going to be based on that location, and alert times we would calculate in that instance would be based on a distance from that epicenter.
But I think that brings up a great question too, just from my perspective of how the shaking you feel is ultimately dependent on how far you are away from not just that point source, but also from the rupture itself. So I think it's a communication issue too. I think, Bob, you would agree with that, but
absolutely, yes.
Yeah. So it becomes a very big communication problem. But both of you might be able to answer this question from Joe Ferrugia. How many full-time staff are dedicated to maintain and test the ShakeAlert system?
That's a good question. And I draw a distinction between, well, okay, it's a complicated answer. I'll try and make it as simple as I can. Remember, it's built on top of the existing network. And there are already lots of people involved in the maintenance of the stations, the telemetry systems, the computer infrastructure, and so forth, just for the routine network operations. And so on top of that, we're adding additional staff for the extra burden of the new stations, for the speed requirements, for the new computers to do this piece of the network task. And then, so there's just the operational component. And on top of that, we have research that's going on. So we're funding research actively to get this done. We're funding people on the CEO side to get this done. So there are lots of folks involved. And the other thing to keep in mind is that our staffing plan, actually, I just found the right resource. Our goal, if we were fully funded, would include approximately 70 additional staff motivated by the increase in the size of the network, the increased burden of the IT, and the CEO part of it. Right now, we have added about 16 people to the network operations to get to where we are now.
Bob, do you have any additional comments to that, or?
That's a good answer.
Okay. Okay, and this is our final question that I received. This is from James Peshman, I think. The Mexico City early warning system disseminates warning uses sirens and loudspeakers. Are there any similar plans for the ShakeAlert warning system?
We get that question a lot. It should be understood that Mexico did not build their siren and an alerting system for early warning. It was built for general security and monitoring of folks in the city and communication to people in the city for all sorts of hazards and issues and crime and so forth. So it's an extremely expensive thing to do, and it was motivated by primarily other things other than earthquakes. There are a few siren systems in the US on the West Coast. The ones I'm most familiar with are not yet fast enough to send the alerts in a timely fashion for early warning.
Okay. Great. Well, thank you so much to both of you, Doug and Bob. I greatly appreciate you doing this webinar today, and what a great Q&A session as well. Again, this was recorded, and I'll make it available on our YouTube channel. So thank you everyone for attending, and take care and have a great rest of your day. Thanks.
Thank you, Danielle.
Thank you so much. All right, take care, everyone. All
Bye.
right. Bye.